Today we're going to take a look at section 4.2. And hopefully if I ask somebody, what did we do in 4.1, you would be able to tell me. And everybody, oh, I'm not going to make eye contact. But as soon as I say something like inverses, okay, so from 4.1, we did inverses. And all of a sudden I'm, oh yeah, switch X and Y to help me find the inverse. The symmetry was over the line Y equals X. You know, and we had something like, if I had this, then I'd have that. So in a nutshell, like Austin Powers once said, help, I'm in a nutshell. We did some things like that in section 4.1. We were dealing with inverses. Inverses don't go away. You'll see them again in trigonometry. And I think most of you have to take that course as well. Some don't. But anyhow, section 4.2. Today, you notice I'm just starting with some freehand notes because the lecture notes miss some things that I think is kind of important. We did y equals 2x plus 4. And I want to go back and take a look at that. And I hope you remember that several times I said, I'd rather see it written like this. Okay, because if I picked points 0, 1, and 2, and I looked at the graph goes 1, 2, 3, 4. At 0, it's 4. Boom. At 1, it's 2 more. Takes me up to 6. At 2, there's 2 more than that. It takes me up to 8. And in a world of data analysis, okay, this can go back to talking about something called an initial value. Okay, I start at 4. We gave it the name y-intercept, which is kind of boring, but initial value I like a little bit better because this is where I start. And every time I move over 1, I add 2. So my initial value was 4. At 1, I added 2. At 2, I added 2. At 3, I'd add 2. And this is repetitive addition. Okay, I added the initial value. In our math world, like I said, we call it the y-intercept, and then I keep adding. Okay. Does that make sense? And again, I like b plus mx over mx plus b because again, if you're working with data, this is where I start, and I keep adding something. You know, I had 4, then I had 4 plus 2, then I had 4 plus 2, and I added another 2. And then the next one would be 4 plus 2 plus 2, and I would add another 2, and I would just keep going that way. Repetitive addition. Now, why do I do that? Well, it's going to help me explain a little bit better about an intro to these things called exponential functions. Function. Okay, these guys were called linear. Uh-oh, my pen is dying. Linear functions. It's coming back. Okay, so far, are you with me? It's kind of clear, right? I have an initial value and I keep adding something each time. Well, an exponential function is really the same thing, except instead of adding, I'm multiplying. I start with an initial value, maybe 2. And then I'm going to multiply by something. Let's say I multiply by 2. So my next value would be at 4. Okay, let me write some of this down. At 0, I was at 2. That was my initial value. At 1, I'm now at 4. At 2, instead of adding this time, I'm multiplying. I'm going to double it. I'm going to double it. So at 2, 5, 6, 7, 2, I would be at 8. And it would grow exponentially. You know, 2, I'm at 8. So again, I started with an initial value of 2. Then the next time I I can't see it, I'm sorry, multiplied by 2. Okay, so that was at 1. The next time I multiplied by another 2. And I kept multiplying by 2. I probably should have started this at 3 or some other value to change it. Here's an initial value of 3. And let's say I multiply. So the first one's at 3. If I'm multiplying by 4, the next one would be at 3 times 4. Then 3 times 4 times 4, and so on. So if I get ready and put this back together, I have my initial value. I'm looking at this instance. And then this was at 0. This was at 1. It gave me a 4. This was at 2. It gave me 2 4s. The next one would be at 3. It would give me 3 4s. Give me another way to write this. Give me like a generic version of this so that, you know, here's 3. Here's 3 times 1 4. Here's 3 times 2 4s. Here's 3 times 3 4s.
That'd be 3 times 4, 3 times 4 squared, 3 times 4 cubed.
Right. Or 3 times wherever I'm at, and we're going to call that 3 to the x power. So it's going to be 3 times, and all I'm doing is reducing 4 times 4 times 4. Just like up here, we reduce 2 times 2, or 2 plus 2 plus 2. There's 3 of them. That's the same as 3 times 2. Down here, there's 3 of them. That's like 4 cubed. So the difference between the linear is that it's y equals b plus, I'm adding x's, and down here in my exponential, it's y equals, and in this case, it's called a c for the initial value, but instead of plus, it's times this 4 to the x kind of deal. Okay, and we're going to represent that with a little a. So the same. They start with something. This is repetitive addition. Starts with something. This is repetitive multiplication. So the two are actually really related. And hopefully that's going to make this look sense. This C, same as B. It's my initial value. It's my initial value. This A is actually called a growth factor because I'm growing by that much each time. All right, so I wanted to throw that out as an initial look-see before we get ready and we talk about what the graphs of some of these look like. And again, I look at this, f of x equals 3 to the x. I'm going, it's missing something. This really should be 1 times 3 to the x. I already know if I put 0 into that, it's going to be 1. If I put 1 in, it's 3. 3 squared is 9. 3 cubed is 27. And we see, and it's taken off. Boom. What if I put -1 in? I'm allowed to do that. 3 to the -1 power. This is 3 to the well, that's 1/3. Negative exponents. So that would be down in there. And oh yeah, this is going to be something like we just had. It's approaching that asymptote, the line y equals 0. Okay? So that's what the graph looks like. Again, I start with an initial value of 1, multiply by 3, multiply by 3, multiply by 3, and it's rewritten this way. Well, this next one, they get a little goofy on us. You know, and again, I don't know why, but if it's a negative exponent, first of all, my initial value is going to be 1 again, because it's not no numbers there, so it's got to be 1. 2 to the -x is the same as 1 over 2 to the x power. Well, let's see. If I'm at an initial value of 1, I know that. I'm going to keep saying that. So when x is 0, that does become 1. When x is 1, that becomes, I believe, 1/2. And if I mess that up, somebody will let me know. Uh-oh. What if I'm going the other direction? What if I put in -1? 1 times 1, 2 to the -1. That's 1 times, I would flip it. Oh, that's 2. So -1, I'm up at 2. And all of a sudden I'm saying, okay, at -2, I know where I'm going to be. I'm going to be up at 4. Again, it's going to come down to that asymptote. Okay, so we have a decent idea of what they look like. I don't see any head shaking, but I'm assuming they're all shaking yes. No one shaking their head no. No, we're not doing that. We're not doing that. We need to learn about exponents before we get into translations, because this would take it and flip it and shift it up 1, that whole idea. But we're not really ready to do that yet. Okay, any questions? And again, you see it listed here. There's my H, there's my A, there's my K. So if I went back up and rewrote this, -2x plus 1 on the end, there's that K that would move it up 1. This would move it left 1. This would flip it. So hopefully you got that earlier, and we're not really going to get into that so much right now. Okay, so I'm going to be dealing with the exponents, and we get this certain special value. It's called E. And it's going to become really important when we talk about exponents, because exponents go one direction. And then, believe it or not, we're going to talk about their inverses, and they go back the other direction. And we're going to see the relationship between an exponent and a logarithm. Some of you are familiar with the term logarithm. No worries, Radhika. I'm just glad you're here. Okay, so I come down here, and there's this letter. Now, we already know something called I. That's the square root of -1. It's special to us. Well, there's another letter, lowercase e, that is kind of important in the world of exponents, as I said a moment ago, and it's called E, short for exponent. But E is this. If I took a look at this guy, 1 plus 1 over x to the x power, we call that E. And if I calculated it, well, what do I mean by calculate it? Well, if I took this and said, well, you know, I'm going to put in 1 and I get a value, and I'm going to put in 2, and then I'm going to put in 1,000, and then I'm going to put in 1 followed by a whole bunch of zeros. As I continue to put numbers in here for x, my y's will actually get closer and closer to this value, 2.718281828, yada, yada, yada. It's a numerical representation for E. You notice the squiggly lines. That means approximately. That's not an exact value. That keeps going on and on and on. All right, so we have some practice with E. What is E squared? I don't know. I'm going to turn this on, and I'm going to say, good morning, computer or calculator, and I clear, and I want to do E squared. So now first thing I have to do is find E, and I'm going to ask, does anybody know where it is? I'm looking over my graphing calculator, and I think I see it. Is it above the division sign? Second divide, and there's E, and now it wants an exponent. If I said E to the first, I did E1, 2.718281828 kind of deal for me. If I do E, second divide, squared, I get 5.43659. So I can come in here and, this is going to be 5.4365. And I'm just going to go 3 decimal places, 5.437. Okay. 3 decimal places, always good to go. And I could continue. I could throw in -3, nice and simple. Second divide down below here. I'm going to do parenthesis, -3, and enter, and I get a value, -8.
Professor,
Yes.
you're doing e times 2, not e squared. E squared 7.3891.
You're exactly right. I need to do second e raised. See this right above here, right here? Squared. Now, if I hit enter, I get the right answer. Sorry about that. Thank you. Does everybody see my mistake? I did e and 2, and it just multiplied it by 2. Scratch, 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 scratch. I needed to do e, which is above the division sign, and then caret to let me square it. Thank you for that. Now we don't have to come back and redo them all. Squeak, 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 squeak. 7.389. You got the idea? As I said, I'm not going to do all these. You could do them on your own. Unless somebody wanted me to actually show e to the square root of 7 or e to the pi.
Can you show it again, please?
Okay. Let's do e to the square root of 7. I hit second divide. That gives me e. I'm now going to hit up arrow, and you'll see that this made a little box up here and is sitting up there. Now I want to do square root of 7, and the square root is down here with the x squared key. So I'm going to hit second x squared. That gives me the square root, and there's 7. 14.094. Does that help, Radiga? I think she said yes. Do 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 do. Do 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 do. Do 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 do. Same thing we've been doing with graphing. Pick a couple of points, not something that I want to get into right now. Now, boy, oh boy, oh boy, they don't waste any time with the way they lay things out. This exponential function is going to let us work with interest, compounding interest. And oh my goodness, all of a sudden I see a whole bunch of stuff. Usually when I jump into the problem, I can figure out what it is right away. All right, so let's do some scratch work here. At $15,000, okay. Thank you very much. It is at 2.5% interest. And it talks about stuff for 7 years. How much will I have at 7 years? That means I start out with 15,000. Agreed? And at the end of the first year, I'm going to have 15,000. And then I'm going to be kind of like adding 2%, 0.025 of the 15,000. Okay, times the 15,000. So I start with this. That's my initial value, right? Oh, wait a minute. Yeah, I got that going. That's my initial value. Okay. And at the end of the first year, I have something that looks like this. Well, in my math world, I can clean this bad boy up. I can say, wait a minute, this equals, I'm going to factor out 15,000. And what am I left with? I'm left with a 1 plus 0.025. Ah, that's kind of interesting. The 1 is the original amount. The 0.25 was my rate of increase. Okay, it's an extra amount that's being added on. Are you with me? So here was the first year. It improved at the initial value. It improved at the end of the first year to this amount. Okay, I could do the work on that if I wanted, but my second year is going to be take this amount right here and do the same thing I just did up here. So in place of the 15,000, it'll be this. In place of this 15,000, it'll be this. So it's going to be, in place of this, it's going to be 15,000,000,1.025. Okay, so it's that amount plus 0.025 again times that last year, which was 15,000 times 1.025. So at the end of the first year, that's the nice clean one, okay? Well, check it out. At the end of this year, I'm going to be able to pull out that 15,000, 1.025. And what am I left with? Well, if I pull it out of here, it's a 1. If I pull it out of here, it's a 0.25. And all of a sudden, this becomes 1.025. And this was 15,000, 1.025. Huh. Or writing it exponentially, 1.025 squared. First power. Year 3 would be cubed. So yeah, I'm taking my 15,000 and multiplying it by 1.025. I don't know how much money that is, but it'll be nice. The next year, I'm taking that value, which was here, and I'm multiplying it again by 1.025. So I end up with a function that looks something like 15,000 times 1.025 to the year power. At 0 years, this is 1, it's 15,000. At 1 year, I would plug it in. At 2 years, so not only am I getting interest on my 15,000, when I get to this next year, I'm getting interest on my interest. And it's going to keep increasing over and over and over. So I'm going to do this on the calculator. I have it on. Keep an eye on me so I don't screw it up. 15,000 was my first year times 1.025, which was my percent of increase, which was kind of nice. So now I have at the end of the first year, 15,375. So it went up $375. Now at the end of the next year, so I'm going to take that answer and multiply it by 1.025. It becomes $15,759.30. What's a bank going to do? Are they going to round up or down? They're going to round down. You see that extra 5 out there? Somebody gets that. And there's movies made about it. But my first year was 15,000. That's what I started with. The end of the first year, it went up 375. You notice it didn't go up another 375. It went up a little bit more than that. And again, the reason is it's interest. It's interest on the interest that I made. And it would continue to grow. So here's my equation. Initial value, 15,000. My rate of change. My rate of change. So we're looking at this in reverse. When I have 1.025, my rate of change is 2 decimal places, 2.5%. Okay, what if I said it's increasing 1.1? What is my rate of change? Two decimal places, right? We went 2 decimal.
100%.
Well, not 100. You're really close. This is 10%. Okay, and here's how we're doing it. It's 1 plus 0.1, and 0.1 is 1/10, 10 over 100, 10%. So if I increased by 100%, 100% is 100 over 100. That would be 1. That would mean I would have a 2 there. Kind of idea. I know this is a lot. This is a lot real fast. What if I went the other way? What if I had 0.9? Well, wait a minute. That's not plus. That's 1 minus 0.1. 0.1 is actually, I'm going down 10%. It's going down. It's decreasing. 0.85. It's down 15%. Okay, so this number is actually really interesting in a lot of real life problems where we talk about exponential growth because it's growing. And what's the term here for when it's going down? Instead of exponential growth, it's called exponential. Did you ever hear the term exponential decay? I hope so. Okay, so if I come back over to my notes, if this is compounded annually, that's kind of nice. Compounded annually, we just said what do we want to call this? Determine the amount. My amount is equal to the 15,000 times 1.025 to the year. And if the year is 7, how much do I have? All right, this is another calculator problem. I'm going to do this first. 1.025 raised to the 7th power, enter, times 15,000, enter. 17,800, $17,830.28. Again, the bank's not going to round up. They're going to keep your partial pennies. So yeah, nice. That's a pretty good return on your investment in 7 years, almost $3,000. That's kind of nice. Okay, so that would be what we're looking at up here. And, you know, I'm happy with that after 7 years. Okay, now this guy says compounded continuously. Well, that's this equation right here. That's this equation right here. Okay, it's called PERT. A equals P, and then it's that E we were talking about raised to the RT power. Now that comes from somewhere. That comes from something similar to here, but it's instead of, well, really we should do B first. Let's do B, okay? So if I get ready and do B, my amount, and this guy is compounded quarterly, which is the second formula. Okay, let's see how it works. 15,000, and then in the parentheses, I have the 1 plus. Well, if it's compounded quarterly, that means I'm not getting 2.5% every quarter, I'm going to get that, I'm going to divide. So 0.025 divided by 4. Because I'm doing it every quarter. Now, how many quarters are there in 7 years? If there's 4 in 1 year, how many in 7 years?
28.
28. So that's 4 times 7. So this quarterly breaks it up into, it's doing it every 3 months, 28 times. So when you look up here and you see P parentheses 1 plus, we're breaking the rate up by dividing it by 4 since we're doing it quarterly. And then the number of times I do it will be 4 times 12. If I did it monthly, I would be replacing these 4s by what?
12.
Yeah, by 12. Yep. And again, why is this better than this? Because I am getting more interest on interest. So let's see, amount equals. All right, I need to figure out a good strategy here. I'm going to work from the inside out. 0.025 divided by 4, and I get that answer. Add 1. I get that answer. Now I'm going to raise to the 28th power. Okay, put 0.025 divided by 4 first. Then I added 1. Now I'm going to raise, that's my caret over there. Notice how it brings the answer, the previous answer right up for me, to the 28th power. And I get an answer. Now I'm going to multiply that by my 15,000. 17,858.96. Yeah, buddy. That's a little bit better than this. It's $28 better because I'm getting a little bit more interest on interest. Not a lot, but it's better if it's compounding quarterly. Now, what if I took that formula? I'm going to do this in red. That formula right there, puberty, 1 plus R over N to the NT power. And if there's a little bit of algebra that goes on here, and we start talking about something called a limit, because now my N is continuous. So it's the limit as N, you don't need to know this. So N gets larger and larger and larger and larger, and basically you are getting interest immediately upon, so instead of calculating 4 times a year, it's called continuous. And inside of here, because of the way all this works, we get the 1 plus 1 over N to the N power, which earlier we said is E. And you start to see it in here, and all of a sudden it becomes the principal, which is the 15,000. And it's this new formula. So because of all this stuff going on down here that we're not going to get into, but you do see that E is in there, 1 plus 1 over N to the N. And as the N's get huge, 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 that 1 and that part give me the E. And we do a little bit of work here, and we end up with PERT. In the old days, people knew it because it was a shampoo. So if this is compounded continuously, that's yearly, and that was good. This is quarterly, that was good, better. Now I'm going to have 15,000 times E raised to the R, 0.025 times T, 7 power. Well, I hope I'm getting something in the range of a little bit more than this. I'm going to do this first. I'm going to get my E back. Second, divide gives me E. Raise to the, and let's see, I need 0.025 times 7 power. Enter. Now I'm going to multiply that by 15,000. And I get an answer. 17,868.96. 0.69. And as I said a little while ago, it's going to be a little bit better than this. And in fact, it is almost $10 better. So annually was nice and simple, right? Annually was nice and simple. It was my exponential formula, my initial value, my rate of change, over and over and over again. We did that on the paperwork. That was a bunch. That was a bunch. Weapon grade plutonium is composed of blah, 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 the half-life, blah, 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 and the blah, 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 blah. And oh, fortunately, they give us a formula. Okay, now let's talk about this. Initial value, 0.5. You know, so if I'm looking at this on a graph, here's one, my initial value is that. And you notice this. Earlier, we had things like 1.025 and it was going up 2.5%. This is 1/2, which is 0.5, which is the same as 1 minus 1/2. This guy is going down 50%. And that's where this term half-life comes in. I keep multiplying by 0.5, 0.5, 0.5. Okay. So the half-life of this type of plutonium is 70 or 24,000, yada, 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 yada. And I'm given a formula. A sub T equals 0.5, excuse me, times 1/2 to the T over that. Okay, you notice how I'm dividing by 24. Weapons grade plutonium is the amount left after 2 years is given by that. So if I put in 24,000 for T, I have 24,000 divided by 24,000, which is 1. 1/2 times 1 is 0.25, 1/2 of a half. So as you can see, in 24,000 years, my original amount, which was 0.5, is now down to 0.25. So there's still some of it hanging around, 1/2 of what we started with. It just slowly degraded. What if after 72,000 years, how much of my original plutonium, 0.5 kilograms, right? We're now down to 0.25 kilograms. Well, that's that. And that's going to be 1/2 is also 0.5 raised to the 72,000 over 24,000 power. 0.5 times 0.5 raised to the, I can drop all those zeros. I can say this is 72 over 24. So I'm going to do that on my calculator. On 0.5 raised to the parenthesis 72 divided by 24. Some of you already might know what that is. Enter. Then I'm going to multiply that by 0.5. And it looks like 0.0625 kilograms will be left of plutonium. So what's going on here is it just keeps dividing by 1/2 year after year after year. Population grows exponentially. I've done way too much talking. I'm going to pause. So I asked and I got the answer, 115.4796. I started with 111. After 4 years, my population is 115.4796 million people. 115,476,600 people. Did anybody get a different answer? Did anybody get the same answer?
Yeah, that's what I got as well.
Excellent. Can someone put in the chat what they got for B? After 75 years, 75 years. So this was in 2010 when it started. 4 years later, this is 2014. 75 years later is going to be in the year 2085. The population of Mexico will be, looking for a drum roll, looking for an answer, looking for some love. There's an answer. 233,072,470. 0.5 people. Somebody else get that? Thank you, Kaylin.
Yeah, that's what I got as well.
Excellent.
Yep.
Who is this 0.5 person? Interesting, right? Interesting when you start. So, man, I'm thinking that the population is going to more than double in 75 years at this rate. We probably don't want to have people. We probably want to erase that. Leave that out. Good. Good.
Could we round up for that, or would we just get rid of it?
6 of one, half a dozen of another. That's up to you. Yep. Okay. That was interesting. What we're going to start doing next week on Tuesday is we're going to start looking at equations with exponentials and how we can work with them. But I think right now you got a pretty good idea. And the gold was when we hit this problem down here in the bottom. That number 9, that was the one that we were cracking our knuckles and we were all happy about.